So common negative feedback op amp circuits. So we're going to start with number one, and I will give it a name after we analyze what it does. Okay. So the first circuit that we're going to look at is actually something that you guys saw on the in-class assignment and the homework set, with a couple of very, very minor modifications here. So for this first circuit, we are going to connect our non-inverting input terminal to ground. We are going to have a feedback resistor, which I'm going to call R2 here, connected between the inverting input and the output node. We are going to measure our out voltage at the output terminal. I'm going to place a resistor R1 between the inverting input node and our input signal. The end. Like so. So we're going to figure out how this thing works just by using the exact same three-step process that we developed in our last class. But we are going to have a generic relationship that's going to relate the resistor values R1, R2, the input voltage Vn, and the output voltage Vout to each other. So effectively, we're figuring out what the transfer function of this system is. All right. So our first step is always to apply op amp rule number one and observe that no current can flow into either input terminal. And then we determine what our voltage is at our non-inverting input terminal, which by inspection here, we can easily see is 0 volts. Our second step is to apply op amp rule number two, which says that the voltage present at the non-inverting input terminal has to be the same as the voltage present at the inverting input terminal. So that tells us that V minus is also 0 volts. And now we're going to write a Kirchhoff's current law expression. So we're going to say that this current leaving our inverting input node plus this current leaving our inverting input node must be equal to 0. So that's going to look like 0 minus Vn divided by R1 plus 0 minus Vout. So minus Vout over R2 is equal to 0. And with just a little bit of algebra, we find out that Vout is equal to negative R2 over R1 times V. So this amplifier is what's known as an inverting amplifier. It is an inverting amplifier because a positive input signal generates a negative output signal. And the voltage gain of this circuit, so let's define what that is. So A is the symbol typically associated with gain. Subscript V denotes that we're dealing with a voltage gain. And this is mathematically defined as simply the ratio of the output voltage to the input voltage. And so for this particular circuit, that is nothing more than the quantity R2 over R1. So the gain, or the amount of amplification that this circuit provides, is dependent only on the size of the resistor values that we choose. Okay. So that means this amplifier circuit can amplify signals and make them larger if R2 is greater than R1, And it can be also used to attenuate signals or make them smaller if R2 is less than R1. So we get a lot of utilization out of this. The quote unquote drawback from this wide application is that we invert the polarity of our signal, okay? So if we wanted to design an amplifier that boosts our signal by a large amount, we can achieve that by either making R2 much greater than R1 or making R1 much less than R2. So that's our first. The second circuit that we are going to analyze is going to look extraordinarily similar, but there's one fundamental change here, okay? So here's my op amp. I'm going to have my feedback resistor once again placed between the inverting input terminal and the output terminal, like so. I'm going to call this R2. I'm going to measure my output voltage at the output pin as per usual. I'm going to have a resistor between the inverting input node. And instead of applying my input at the other leg of this resistor, I'm going to ground it. I'm going to place my input signal now here. So the only difference between these two circuits is that ground, sorry, my arrow isn't as good as I want it to be. Ground and my input signal have switched places. It's the only change between these two circuits. I'm making a big deal about that because you are going to be asked to build both of these circuits later on today. And some of you are going to do something very dumb and completely tear apart your entire circuit to rebuild it to switch to the other one, when if you do it smartly, you can literally swap two wires to get the same result. So do not tear everything down. It's a huge waste of time and opens yourself up to making simple connection mistakes. So anyway, all right, so I'm going to apply op amp rule number 1 and observe that I have no current flowing into my input terminals. My voltage present at my non-inverting input terminal must be the quantity V in this case. When I apply op amp rule number 2, I notice that there is a voltage of V in present at the inverting input node. Now I can apply Kirchhoff's current law. Sorry, my multimeter over there is beeping a bunch. It'll sort itself out momentarily. So if I apply Kirchhoff's current law at the inverting input node, I will have V in divided by R1 plus V in minus V out divided by R2 is equal to 0. And after a small amount of algebra, what we will find is that V out is equal to 1 plus R2 over R1 times V in, which means we have a voltage gain. V out over V in is equal to 1 plus R2 over R1. So in this particular circuit, it only provides amplification. We cannot make our output signal smaller than our input signal. It's mathematically impossible, okay? So we can only scale the output. If R1 is much greater than R2, our gain is approximately 1, and this amplifier can be used as what's called a unity gain buffer amplifier, which is a critical amplifier for many types of instrumentation and control systems. Effectively, what a unity gain buffer does is it allows you to use a sensor that is only capable of generating a small amount of power and replicates that signal at the output, but allows the power supply to provide any necessary current that is needed further down the line, so that you're not relying on your sensor to generate the current to drive your system and all that kind of stuff. So critical component in a lot of instrumentation and control systems, right? When R2 is greater than R1, we obviously get some type of positive gain, which means we are amplifying our signal. Notice that there is not a negative sign here. So this is what we're going to call a non-inverting amplifier, because when we apply a positive input voltage, we get out a positive output signal. Any questions on either of these two amplifiers? So the remainder of the amplifiers that we are going to talk about are really just combinations or subtle variations of these two. These are kind of the fundamental building blocks for analog signal processing. And beyond this point, even doing things like calculus actually just uses these two types of amplifiers. We're just changing the components that we're using. Okay. So let's look at circuit number 3. I'm going to give myself some room over here. So thus far, what I'm drawing looks extraordinarily similar to an inverting amplifier. I'm going to call this resistor in the feedback loop connected between my inverting input terminal and my output terminal to be RF in this case. You'll understand very momentarily why I'm not calling it R2 anymore. I'm going to measure my output voltage V out here. And now what I'm going to do is I'm going to connect multiple resistors. So let's call this guy R1, this guy R2, and this guy down here R3, between my inverting input node and multiple input signals. So V1 represents an input signal, V2 represents an input signal, and V3 also represents some input signal. Okay. So if we looked at this circuit from a superposition perspective, where we looked at each one of our voltage sources, our input voltage sources were on at a time where the other two were turned off, this is nothing more than an inverting amplifier. And then we could add up the results together at the end. So using superposition, we could say that V out 1 would be negative RF over R1 times our input voltage V1. V out 2 would be negative RF over R2 times V2. V out 3 would be negative RF over R3 times V3. And from this, V out is just the sum of those. So it's going to look like negative 1 over RF times V1 over R1 plus V2 over R2 plus V3 over R3 etc. Okay. We can prove this very easily using our three-step process as well, just for those of you who are not super comfortable with superposition. Okay. So using our three-step process, we can observe that this current is 0 amps. This current is 0 amps. The voltage present at our non-inverting input terminal is 0 volts. Moving on to step 2. Yes. It isn't, it should be RF over. Sorry, I messed up my fraction there. Thank you. Moving on to step 2, we're applying Kirchhoff's current law, and so we're saying this current leaves, this current leaves, this current leaves, and this current leaves. And so what that's going to give us is negative V3 over R3 minus V2 over R2 minus V1 over R1 minus V out over RF is equal to 0. And then algebraically, we would find V out is equal to negative RF times V1 over R1 plus V2 over R2 plus V3 over R3 like we did earlier, or we would have earlier if I hadn't made a simple mistake that Andrew was nice enough to point out. So thank you very much for that. This circuit is what's called a weighted inverting summer or a weighted inverting adder. So this is how addition is performed using an op-amp. We have multiple input signals applied to the inverting input terminal through that simple resistor network there. And our output is effectively a scaled average of whatever the sum of the inputs are, where each of the different input signals is scaled by a different amount, which is established by that feedback resistor RF and the resistor associated with that input voltage. So if we wanted to just have an inverting summer where we didn't want the different input signals to have different weights, we wanted them to all scale by the same amount, we would just make R1, R2, and R3 equal to the same resistor value. Then all of the inputs get scaled by the exact same amount. All right, so we have done addition. Now let's look at this guy. So this one is another one that's going to look pretty complicated. I'm going to start with a resistor R in my feedback loop connected between the inverting input terminal and ground. Excuse me, the inverting input terminal and the output terminal. Pardon my misspeaking there. I'm going to measure my output voltage at the output terminal. I'm going to place a resistor R again. So these two R's have the same value between my inverting input node and a voltage source, which I'm going to call V2. Connected to my non-inverting input node, I'm going to have a little circuit like so. So there is a resistor R between the non-inverting input node and ground. There's another resistor R between the non-inverting input node and a second input signal, which we're going to call V1. We could, if we were so inclined, also use superposition to analyze this guy, okay? So with V1 on and V2 off, this looks like a non-inverting amplifier with a voltage divider circuit at its input. Very similar to what I gave you guys on your in-class assignment problem Wednesday. With V2 off, excuse me, with V2 on and V1 off, this looks like a simple inverting amplifier. So what we're going to have is some subtraction operation that's going to go on. Now let's use our three-step process to more formally look at what's happening here, okay? So if no current can flow here, and no current can flow here, what do I expect my voltage V plus to be? What was that? So it's not going to be just V1. If it were just V1, that implies that no current can flow through. Effectively, the implication there is that this current would be 0 amps, and there's no reason for that to be true. So I will explain it similarly to what we did yesterday for those of you that asked about problem 2 in the in-class assignment. Let's assume that there is some current that's leaving the positive polarity terminal of our input voltage, V1. Okay, we have no reason to assume there isn't. All of the current that leaves the positive polarity terminal of our input voltage, V1, flows through that horizontally oriented resistor R. None of it can branch off and flow into the non-inverting input terminal, so all of it must flow down through that vertically oriented resistor R to ground. And then we complete the loop by connecting our grounds together. So we have some circulating current flowing in that loop. Observing that, what do we believe the voltage present at our non-inverting input terminal should be? Half of V1, absolutely correct. So just using good old voltage division, the voltage present at our non-inverting input node should be 1/2 of V1, because exactly half of the voltage drop occurs over each of those two resistors. So we have V plus is equal to 1/2 V1. And then V minus must also be equal to 1/2 of V1 because of op-amp rule number 2. Okay. If we apply Kirchhoff's current law, adding this current plus this current together, what we will get is 1/2 of V1 minus V2 divided by R plus 1/2 of V1 minus V out divided by R is equal to 0. If I multiply both sides of this equation through by R, I get 1/2 of V1 minus V2 plus 1/2 of V1 is equal to V out. And therefore, V out is simply V1 minus V2. If all of my resistor values are not identical, it does not work out this neatly, okay? We can do weighted subtraction and things like that if we wanted to, but I would argue that it's much easier to do a simple subtraction and then weight it using an inverting amplifier or a non-inverting amplifier later on than it is to do the math of figuring out what happens when all these resistor values are different. It gets really nasty really, really quickly. So having a two-stage amplification circuit is a much better option if you need to scale your subtraction operation. It's much easier to follow what's going on. Okay. So to this point, we have talked about how we make signals larger and smaller using amplifiers, how we perform the mathematical operation of addition, and the mathematical operation of subtraction using op-amp circuits. Multiplication and division cannot be done with a single op-amp, so we are not going to talk about those. That being said, excuse me, my nose is bothering me. We can do the calculus operations of differentiation, or taking the derivative of an input signal, and integration of an input signal just using a single op-amp. So let's look at our last two circuits. Sorry, I didn't give this guy a name, so we're going to call this a differencing amplifier, because it gives us the difference between two input signals. I'm going to have a resistor R in my feedback loop for this guy. Here's where I measure the voltage V out. And instead of placing a resistor here, I'm now going to place a capacitor. And my input signal needs to be some function of time, so it needs to be time varying in order for this circuit to work correctly, because if it were a DC input voltage, the capacitor would only see, it would look, behave as if it were an open circuit and wouldn't actually do anything, okay? So just as a quick reminder, we know that current flowing through a capacitor is given by C dV by dt. And alternatively, we know that the voltage drop across a capacitor is given by 1 over C times the integral from -infinity to t of IC of t prime dt prime. I'm using this particular representation of the integral so that I don't have to think about what the initial condition does on the circuit. So it's purely just to make the math slightly easier, okay? So while I am at it, I'm going to call this voltage VC of t. And this current IC of t. We're still largely going to use our same simple three-step process to figure out what the heck this thing does, but we're going to have to also tie in our relationships for how a capacitor behaves, okay? So applying op-amp rule number 1, we know that there are 0 amps of current flowing into either of my input terminals, and I can observe by inspection that my voltage present at my non-inverting input node is simply 0 volts. Applying op-amp rule number 2, I know that the voltage present at my inverting input node must also be 0 volts. So from here, I'm going to apply KCL, but I'm going to do it slightly differently. I'm going to say that my current IC of t, the current flowing through my capacitor, has to be equal to the current that's leaving my node. So I'm saying this current in equal to this current out. The current that's leaving is negative V out over R. Everybody okay with that? Just 0 minus V out divided by R. Good old Ohm's law. Nothing wild or crazy there. So what we're going to do now is we're going to substitute in that first equation that I have written in the top right-hand corner that tells me what my capacitor voltage is as a function of my, it tells me what my capacitor current is as a function of my capacitor voltage. So we could say that C dVC by dt is equal to negative V out over R and from this we could say that V out as a function of time is equal to negative RC times dVC by dt. Everybody okay with that algebraic step there? So the last thing that we need to do here, because we're trying to figure out what the output is as a function of the input, is relate our capacitor voltage VC of t to our input voltage. So what is that relationship? So our input voltage is the voltage present between this node and ground. Our capacitor voltage is the voltage present between the orange node and our inverting input terminal. But our inverting input terminal has a potential of 0 volts. So it serves as a virtual ground. It's not physically connected to ground, but it has the exact same potential. So from that, we can say that our input voltage and our capacitor voltage are actually the same quantity. Vc of t is simply Vn of t. And using that relationship, we get this. So in this particular circuit, which is what we're going to call a differentiating amplifier, the output signal, V out, is a scaled version of the derivative of the input signal. Anybody have any questions regarding this analysis? It's really nothing more than we've done up to this point using that same 3-step process, except that we had to remember what the current voltage relationship for a capacitor was. So our last circuit that we're going to look at is this exact same circuit, except we're going to swap the placement of the resistor and the capacitor. What do you guys think is going to happen? Integration. So if we have the resistor in the feedback loop, we have differentiation. If we have the capacitor in the feedback loop, we're going to get integration out of it. And I'll prove it to you. So our last circuit, a differentiating amplifier. All right, so this is our circuit. I'm going to write down my capacitor relationships again. Like so. I'm going to define my capacitor voltage in this way and my capacitor current in this way. So as always, we are going to start by saying that there is no current flowing into the input terminals of our op amp. By inspection, we can see that there is no voltage at the non-inverting input terminal because it's connected directly to ground. Applying op amp rule number 2, there is also no voltage present at the inverting input terminal. So now I'm going to write my Kirchhoff's current law equation. And I'm going to say that the current in is equal to the current out. So that means V in minus 0 over R is equal to IC. All right, so I need to do things in a slightly different order here. Instead of the last step being relating the capacitor voltage to our input or output, we're going to do it now so that we won't have too much algebraic steps. So VC isn't related to the input voltage in this case. It's related to the output voltage. Can anybody tell me what that relationship is? Absolutely correct. So the positive polarity terminal of V out is this node. The negative polarity terminal of V out is effectively ground or 0 by definition because we're dealing with a nodal voltage. The positive polarity terminal of VC is at ground, and the negative polarity terminal of VC is at the orange node. So VC and V out represent the exact same voltage, but with opposite polarities. So they have to be the same thing, but with an opposite value. So I'm just going to write that down here. V out is equal to negative VC. Well, we know that VC is 1 over C times the integral from negative infinity to T of IC of T prime dt prime. If we substitute in the relationship that we determined was equal to IC by applying Kirchhoff's current law at the inverting input node, we'll have negative 1 over C times the integral from negative infinity to T of Vn of T prime over R dt prime. And now it's simply a little touch of algebra here. So we're going to have negative 1 over RC times the integral from negative infinity to T of Vn T prime dt prime. So our output voltage is a scaled version of the integral of our input voltage. So this is an integrating amplifier. Now, what is so neat to me about these last two circuits is that they have so many uses within the field of electrical engineering, okay? So mathematically, we can easily see how the integration and the differentiation is performed, okay? That's just how the math works out, so that's what it does. So we have these fundamental building blocks of analog signal processing that perform a specific mathematical operation. In the field of communication systems, these circuits also act as filters effectively. So one of them is a low pass filter, meaning that it attenuates signals below a certain frequency. The other one is a high pass filter. That means it passes everything beyond a certain frequency. They are also fundamental building blocks of control systems and all of that kind of stuff as well. So these two circuits here, these last two that we've talked about, behave the same way, but effectively are used in three very, very different aspects of electrical engineering. That's how robust these guys are. We won't actually, so for this class, I'm not gonna make you ever do any of this calculus stuff on your exams or homeworks or anything like that. I just like to show you how powerful an op-amp can be. A single integrated circuit device does calculus for us if we need it to figure out what the rate of change of our signals is and all that kind of stuff. So we could take a triangular or sawtooth wave and make a square waveform or a series of rectangular pulses and vice versa using these. I don't know, just a really important part of signal processing. So I like to talk about it even though we don't actually get to use it in this particular class. All right, so those are the different types of amplifiers that I wanted to introduce to you all today. On your exam, actually, so let's be clear here. This op-amp material will not be on exam 2, which is on Monday. The exam 2 material stopped when we finished transient analysis, okay? So your exam 2 only covers Thevenin and Norton equivalent circuits, both with and without dependent sources, inductors and capacitors, all that associated stuff, and then transient analysis of RL and RC circuits. That's it, okay? You should expect 2 to 3 circuits to analyze for the Thevenin and Norton equivalent circuit parts, 1 circuit that doesn't have dependent sources, 1 circuit that does have dependent sources, possibly 1 circuit that only has a dependent source, and I just want you to find the Thevenin equivalent resistance using the test source method directly. I am not writing the inductor and capacitor problems. That's Dr. Cronk and Dr. Swanbaum's deal. And then for the transient analysis stuff, there's going to be 1 circuit that's an RL circuit and 1 circuit that's an RC circuit. And it'll be broken down into multiple steps that effectively line up exactly with the way that I taught you how to do it. Figure out what's going on at 0 minus, figure out what's going on at 0 plus, figure out what's going on at infinity, calculate the time constant, plug stuff in. So we will have a review session on Monday morning as our regular class meeting, and then you'll be expected to take your exam Monday evening. My understanding is that it is located in the exact same place as it was last time, but I will confirm that with the administrative assistant who figures all that kind of stuff out and send you guys an email over the weekend or Monday morning or something like that. All right, so lab time. Let me go fetch my grad student who's lurking in the back.